Welcome back. This is part 7 of a 9-part series on completing the square. In this video, we'll reflect on what we've learned so far, and we'll discuss how to complete the square symbolically. Get some paper and a pencil, and let's get started. Let's look back at what we've accomplished. If you followed this series and practiced the skills, then given an equation in the form ax squared plus bx plus c equals 0, you can pick any numbers for a, b, and c, complete the square, and solve for x. We've learned how to deal with a wide range of possibilities: constants on the wrong side, leading coefficients, and odd and fractional linear coefficients. You should be proud of what you've accomplished. Every now and then, pull out this equation, make up some values, or better yet, ask someone for some random values, and see if you can solve it. It's also possible to do this without values for a, b, and c. So let's complete the square and solve for x, but instead of using numbers, let's keep the symbols. Instead of finding an x for a specific set of numbers, let's find x for any values of a, b, and c. This would be a general solution. Symbolic problem solving can be very intimidating if you've never done it before. The idea is that you use the same procedures you would use with numbers, but with the symbols instead. We start off with ax squared plus bx plus c equals 0. Like we did earlier, we need to get it to match the pattern in the blue box. First, we move the constant term to the other side. When it arrives on the right-hand side, it becomes negative. We then see that we have a leading coefficient a, so we divide each term by a. The a's in the first term cancel. We are left with x squared plus b over a times x equals negative c over a, which is the pattern we need to complete the square. Let's compare this to our perfect square pattern. We immediately see a problem. In the pattern, we see the symbol b, but this is not the same b as in our problem. So let's use a different symbol. Instead of the letter b, let's use a bumblebee. That's better. According to this pattern, bumblebee is equal to b over a. Then using the fact that dividing by 2 doubles the denominator, we find that bumblebee over 2 is equal to b over 2a. We plug b over a and b over 2a into our pattern. We see from this pattern that if we add b over 2a in parentheses squared to both sides of the equation, we can complete the square on the left-hand side and get x plus b over 2a, that whole thing in parentheses squared, equals negative c over a plus b over 2a in parentheses squared. We can take the square root of both sides and include a plus or minus on the right-hand side. On the left-hand side, the square and the square root cancel. We get x plus b over 2a equals plus or minus the square root of negative c over a plus b over 2a in parentheses squared. We can move the b over 2a to the other side, but when it gets there, it becomes negative. As is the usual style, we reorder the terms by bringing the negative b over 2a to the front of the expression. We've solved for x and found x equals negative b over 2a plus or minus the square root of negative c over a plus b over 2a in parentheses squared. I've written out the two solutions on the right. Let's think about where we started with this problem. We started with ax squared plus bx plus c equals 0. Let's say that instead we started off with the equation 3x squared plus 2x plus 5 equals 0. If we compare these equations, we can see that a equals 3, b equals 2, and c equals 5. We could then use the symbolic answer we just found and plug in the values for a, b, and c and find the values of x. This truly is a general solution. Let's do some additional work. Let's see what we get if we combine the terms. First, let's evaluate the square. b over 2a squared is b squared over 4a squared. We can then multiply the first term under the square root, negative c over a, by 1. We want to match the denominators, so we rewrite 1 as 4a over 4a. After we do this, we do indeed get matching denominators. Under the square root, we get negative 4ac over 4a squared plus b squared over 4a squared. Now that the denominators match, we can combine the numerators while keeping the common denominator. We get x equals negative b over 2a plus or minus the square root of negative 4ac plus b squared over 4a squared. The square root of 4a squared is just 2a. And once again, we see matching denominators, which means that we can combine the numerators. When we do that and reorder the terms under the square root, we get x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Do you recognize this formula? This is the quadratic equation. Even though we set out to find the symbolic answer, we ended up deriving the quadratic equation. Completing the square is only one of 3 usual methods for finding the roots of a quadratic function. The first method is factoring, but this doesn't always work because not all equations are easily factorable. The second is the quadratic equation, which we just derived. And finally, there's completing the square. That concludes this lesson. In the next video, I'll show you how to use what you've learned to solve a projectile motion problem, which is a problem commonly seen in introductory physics. See you next time.